Hello, welcome to the course Electronic System Design. In the few last lectures, we were discussing about how to simulate a circuit using LT-SPICE, which is a software for circuit design. First, we saw the operating point analysis, where we are just interested in the steady state value. Then we saw DC analysis, where we can sweep a parameter, for example, temperature or a voltage, to know the circuit characteristics if the values are changing. The third is the transient simulation, which is kind of a real time. You want to see the circuit performance with respect to time. So, how over the time circuit performs, or for a applied signal which is time varying signal, we want to know the output of circuit. And then we saw that there is a frequency domain analysis, because most of the time we are ending up with capacitor and inductor in the circuits. These are always there in terms of parasitics or actual component. So, these components are frequency dependent, and we saw that there is a frequency domain analysis we do to know more about the performance of these components. So, up to now we have seen some examples of transient analysis, DC analysis, how do we sweep or how do we apply a signal. Today we are going to discuss briefly about one example where we are using frequency domain analysis to analyze the circuit. So, we are going to see a circuit which gives in the signal in time domain. However, it is difficult to analyze the signal in time domain, and how to improve the circuit in time domain is very difficult. So, instead of talking into the time domain, we take the output which is already in time domain, we take this output and convert it into a frequency domain signal, and then we can very clearly see what is the problem and what we can improve on the circuit to kind of improve on the frequency performance. So, the very good example of this kind of circuit is filters. For example, we have a low pass filter. So, filter is a circuit which is good to analyze in the frequency domain. It gives the output in time domain, which you convert into the frequency domain. So, first we are going to make a small low pass circuit or low pass filter, which is having some input which is a main signal, and on top we have a certain noise which we introduce, and want to analyze how this low pass filter is filtering out the noise from the input signal. So, this is what we are going to see in the example today. So, let us go to LT-SPICE. So, we open LT-SPICE here and make a new schematic. As a rule of thumb, first we copy the ground, then we take two resistors, one is R1, the second is R2. Currently we are not making a low pass filter, we are making a just simple resistor divider to see that the transient domain or the time domain signal is full of noise. So, we are just taking this voltage divider, and now we take two voltage sources. So, one voltage source is the main signal, and one voltage source we superimpose here as a noise. So, let us connect them together. So, this is so this is our complete circuit. Let us name first the node. This node, let us say I label it V1 or V in. This is the input. Next we label this as output. Resistance value we can take, let's say 90K and 1K or 10K, whatever. So this is a simple resistor divider where voltage we are applying on the top, and whatever we are applying voltage here, that will be divided at the V out in ratio of 10 and 90. This input signal, now we want to make it two signal, one is the main signal and one is the noise. So let's take V1 as main signal, and because we are doing transient simulation, so we go to a time varying signal. Let's say we take a sinusoid signal here. DC voltage, let's say take 10 volt is the DC offset, 10 is the magnitude, and frequency, let's say we take 1 kilo. So this is the sinusoid signal which we are applying. This signal is having DC offset of 10 volt, magnitude is 10 volt, and the frequency of operation of this signal is 1 kilohertz. Now this is in series with another voltage source V2. This V2 we will use it as a noise source. So this noise again is a time varying signal. So we go to advance, we take the sine signal itself. Now the noise does not have any DC value, so we put DC 0. Amplitude is, let's say 2 volt. However, this is very high, but just to see the noise is there, we apply 2 volt of noise, and frequency is, let's say 100 kilohertz. So the frequency is very high because it's a noise. So we want to apply a low pass filter which is going to cut down all high frequency noise. So we put a high frequency noise here, 100 kilo ohm, 100 kilo hertz. Now our circuit is ready, where we have this sinusoid voltage source which has a inherent noise of 100 kilohertz, and this is signal is applied to resistor divider, where output is the node where we take the output. Now let's specify the simulation type. So we go to configure analysis and we go to transient simulation, and we want to simulate this circuit for, let's say 5 milliseconds. So now our circuit is complete. Let's simulate it. We go to this green color symbol and hit the run. So the simulation is complete. You can see on the x-axis you have time, which is a variable here, from 0 all the way to 5 millisecond, and now we need to put the traces over here. We right click here and then add traces. First we see the V input, the input signal which we have prepared, which is a sinusoid signal along with certain noise. So we press it here. If you see, this is a sinusoid wave which is a signal, but this also contains a high frequency noise. You can see by this signal which is changing. You can zoom in here. You can see there is a noise superimposed on the actual sinusoid. So you see this is a sinusoid signal. Now let's add one more graph here, which is the output. If you see, the output is also having this noise, because resistors are not capable of removing all these noise. Whatever is the signal applied on V in, output will be having the same frequency of noise. However, the magnitude will be less because of the resistor divider concept. So, you can see this output which is also time varying. So, this is a transient simulation where we are seeing this output and input in time. With the time, the signal is changing, it's going up and down along with certain noise which is superimposed on the signal. So, now the problem is, in time domain we cannot figure out much how to remove this noise. We are interested only in this main sinusoid, which is like a large signal, and we are not interested, or we want to remove this small frequency which is the 100 kilohertz frequency, which is high frequency here, but the small magnitude. So, this noise we want to filter out. In time domain, it is very difficult to figure out what to do with the circuit to remove it or to filter out the noise. So, we need to take it out into the frequency domain where we can analyze it better. So, this is our signal, which is the output in time domain. Now, we go to view and plot the FFT of this signal, so that we bring this signal into the frequency domain. So, we go to view and hit FFT, and now we need to choose which signal we want to convert into frequency domain. So, this is V out, we click over here and then we see this. So, here if you notice, on the x axis you do not have time, but you have frequency. So, this is 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz. These are the frequency axis, and on the y axis you have magnitude of that particular frequency. So, if you see here, you have one very sharp peak, very big peak at 1 kilohertz, which is nothing but our main signal. If you see our signal, this is our 1 kilohertz sinusoid signal. This is shown here in FFT. This is our main signal which we are interested in. We want to have this signal, but we do not want noise which is at 100 kilohertz. So, you see 100 kilohertz is this point, and you see there is a peak here. This is our noise which we do not want in our signal. We just want a clean FFT where only we have this peak and we do not have this peak on the 100 kilohertz. However, if you see, there are certain other peaks are there. These are small frequencies. The magnitude is very less, but they are still there. These are nothing but the harmonics of these noise, and these are generated in all real time circuits. These also you need to remove from the circuit. So, ideally you want only this peak in your signal, and you do not want any of these peak towards the right. So, you need to make now your circuit accordingly. So, you put a low pass filter. What is a low pass filter? It filters out the high frequency noise, only it passes the low frequencies. As the name says, low pass filter, it means it passes the low frequencies which is here at 1 kilohertz, and it removes all the frequency on the higher side. So, now we want to put certain components so that the circuit behaves like a low pass filter and removes all these frequencies. In time domain, it is very difficult to analyze what we have in hand, but in frequency domain here we can clearly see we have a signal and we have many frequencies starting from 100 kilohertz onward. So we need to put a low pass filter which cut down all frequency, let's say more than 10 kilohertz or 20-30 kilohertz. So anything which is higher than this value should be cut down. So there is a calculation, you can do it on the paper, which is not we are going to discuss here, but we are going to put a low pass filter here which removes all these high frequency noise. So we go back to our schematic, and now we put a extra capacitor, and R and C together, if we put such a way that it works as a low pass filter. We take one capacitor here and we put along R2. So here we have put one capacitor, and the capacitor value I have already calculated by filter design. So you can go through some course on filter design if you want, but it's not necessary to understand this example. And the capacitor value comes out to be around 17.8 or 17.7 nanofarad. So this is the capacitance value I put here. Now this R1 and C1, they act like a low pass filter, and let us see the output now. We again go and simulate this circuit. So now if you see the output signal, let us enlarge it. So now you see the output signal. This does not have much of a noise. You see, this is pretty much clean. There is little amount of noise, it is already there, but this is much lesser than what we were getting earlier. So this is the signal we get after putting this capacitor, and this signal is fairly free of noise. Let us see the FFT of this wave so that we can know how much noise we have removed. We go to view, FFT, and we plot V out again. If you see, this is the V out curve. So if you see, we have only 1 kilohertz main signal which is already here, this we want, and the 100 kilohertz is very less in magnitude compared to our main signal. This is already removed, and you see these high frequency spikes, these are also pretty much removed. So this, the calculation of this capacitor and putting where to put it in the circuit, it's very difficult to get in the time domain. So here you can see in the time domain, we just saw the output signal where we have noise, but it's very difficult to know how to remove this noise. But if you bring it into the frequency domain, then you can clearly see you have a signal which is at low frequency, and you have so much of noise which is at high frequency. So what you need to do, you need to filter out the high frequency component from the signal. So to filter out the high frequency components, what you will put? A low pass filter. Low pass filter will pass only the low frequency, cut down all high frequency signal. And here you can clearly see, once we put a capacitor in series with R1 and parallel to R2, this act as a low pass filter, and we can clearly see in the FFT as well. Now all the high frequency components are removed from the output. So this is how we can improve our signal to noise ratio. We can filter out all the noise from the signal. We can improve our signal to noise. It's very much used in all circuits and system design. Wherever we want to boost up our signal or most of the time after amplifier we generally follow it with low pass filter, because amplifier also increases some noise, so we have to filter it out. So this is the beauty of frequency domain analysis, which are some of the concepts are very difficult to understand in time domain, so we bring it into the frequency domain by using FFT. So this is all about the LT Spice software, which we are discussing from quite some time. We have discussed almost all types of simulations, DC, transient, operating point and frequency domain simulation. Now when we do all these simulations and we make a certain electronic system, the next thing we do to implement this electronic circuit into a hardware. For that we need a special assembly, something called PCB or the printed circuit board. So this is the assembly where you put all our circuits on the hardware when you actually make your circuit. Right now we are discussing only in LT Spice, where we are simulating the circuit to know whether the circuit is okay, perform as per our specification. Once we are happy with this, we want to actually make the circuit in our lab or in our workshop. So that time we make these electronic circuits on a PCB, printed circuit board. So let's discuss little bit about what the PCBs are. So today now we are going to discuss about PCBs, or called the printed circuit board. In short, we call it PCB. This is P, this is C, this is P. So this is printed circuit board. PCB is a non-conductive substrate that mechanically supports and electrically connect the electronic components using tracks, pads and other features etched on a laminated copper sheet. So this is a simple photo of a PCB. If you see here, this green color thing, this is a surface here, this is PCB, where we have this green color thing. This is a thin sheet of substrate which is electrically insulated. So there is no current flow on this green laminate. However, this green color film is actually coated with the copper from one side or both the side, it depends on our circuit, and that copper sheet we specifically etch. So this etching is very selective here. This etching, what we are doing, we are etching in such a way that copper remains only at particular places, which is traces or pads. So here if you see, these are the traces which we have etched out selectively. So copper is etched from this place and left at this point where this make a trace, and now this is conducting. So if we apply a voltage at one side, that voltage will travel all the way through the track to other places. So for example, we apply signal here at this track, that signal will travel all the way from here to here to here to here and to this point. These are called pads. Pads are the landing pattern where we put another component. For example, resistor we want to put, so we can put one resistor, SMD resistor, over here to here. So these are two pads which are used to connect a resistor, and this signal from this track comes to pad and travel through this resistor, goes to the another place. So this is how a PCB actually works. So the purpose of this PCB is to provide mechanical support. So these traces, these are very fine lines of copper. If we do not have PCB, then the problem is they will not be mechanically strong enough so that we can connect them together. So this provides a mechanical support to all these very small, very thin lines of copper, and it connects them electrically from one place to another, and we selectively etch this copper lines on the substrate, which is PCB. For how do we etch this? That depends on our circuit, what circuit we make and what connections we want from one component to another, and there are certain specific tools which we are going to discuss later sometime, that how to design something called a Gerber file, which is nothing but a pattern. It's like a drawing. You use that drawing to etch out this copper selectively. So this is a simple PCB which you may find in almost all the electronic components nowadays. So once we have this PCB, if we are talking this substrate without any components put in, then it is called a PCB or printed circuit board. But if we put the components which we are going to complete this whole thing, once we start putting the components, ICs, resistors, capacitors together, that time it is called the PCB assembly. So there is a difference between what is PCB and PCB assembly. PCB is the substrate without electronic components, and PCB assembly is the complete thing where we have the PCB and all electronic components in place, which is ready to use. So let us write it down. PCB populated with electronic components are called PCB assembly. or we can say PCBA in short. So once we put all the components together, we call it PCB assembly. Now let's see what are the different types of PCBs. So there are mainly three types of PCBs. The first one is single sided PCB. Second one is double sided PCB. And the third one is multi-layer PCB. So these are three different type of PCB we can see from this figure. Here if you see, you have multiple layers shown here. First we discuss the substrate. So this green color insulating substrate, which we are calling FR4. So you have now see the multiple layers of this FR4 here, here, here and here. So now what is single sided PCB? We have only one sheet of substrate and on top we have copper layer only on one side. We etch out the copper layer and we make the traces and put the circuits on these electronic components on top, everything on the one side of this substrate. So this is okay for very small circuits where we have only 2, 3 or 5 components. However, we need to note that the circuit, if it is a planar circuit, you can represent it in a plane, then you can put it on a single layer PCB. The cost wise it is very cheap compared to the other options. So only one surface we are putting all these traces and components together. However, if we have more components, then it is not possible to put all the components on a single surface. The graph may not be planar. So at that point we need to go for one more layer of connections. So that time we can coat this substrate both the side, on the top also with copper, on the bottom also with copper, and etch out on the top as well as on the bottom, or etch out all the traces and connect the components on top as well as on the bottom. So if we have moderate number of components, then we can go for double sided PCB, which is slightly complex than single sided and little expensive than single sided. However, you can include moderate number of components, let's say 10, 15, 20 components, you can put it in the double sided PCB. However, in this figure if you see, we have multiple layers of this green substrate, which is our substrate FR4 substrate. If we have large number of components, for example all these laptops and all complicated electronics, where we want to have so many components, hundreds, thousands of components on a single circuit, on a single PCB, then it is not possible even to put them on two sides of substrate, on top and bottom. We need to have so many layers to connect all these components. Of course, we do with the help of softwares, but using this software only we can optimize the circuit in minimum number of layers, because the number of layers, if we are going to increase, the cost and complexity going to increase. So we want to shrink our circuit in such a way we use lesser and lesser layers. But if we have more than hundreds or thousands of components, that time we have to go to multi-layer PCB, and this is what it is shown here in this graph. We have now multiple substrate. This is FR4 substrate, and one FR4, in between we are putting a copper layer which is selectively etched. We etch this copper layer, make the traces whatever we want, and then put another layer of FR4. So now if you see this copper traces, these are actually sandwiched between two FR4 substrates. So these traces, we do not have direct access to these traces. These are specifically designed to be in the middle only, and in the middle we cannot put the electronic component. These are not available to us. However, they can be used only to connect one side of electronic component to another side. All these intermediate copper, these act as a traces. So you have multiple FR4 here. If you see FR4 of multiple thickness, you can take multiple types of thickness, put them together. Now you have so many traces available. For example, this is one trace, this is this. You have all 5-6 layers of traces. You can design them as per your need and connect the electronic component together. You can put different type of substrate also. For example, this is a different substrate than FR4. You can also put them. Some are compatible, some are not, so that we need to take care. However, this is possible. So this is a multi-layer PCB. We have multiple layers of copper to connect. This is layer 1, layer 2, layer 3. So for example, this is a 6-layer PCB. You have 1, 2, 3, 4, 5, 6 layers of copper. So this is a 6-layer PCB, or we generally call it multi-layer PCB. Here if you note down one more thing, the dimensions here are most of the time given in mils. In PCB design, most of the time we do not work with millimeter as a unit, we work in terms of mils. So what is a mil thickness? So what is a mil thickness? So mil thickness is common measurement in manufacturing. Whenever we are doing production or manufacturing, those dimensions are mostly given in mils, and a mil is a unit of thickness equal to 1,000th of an inch. It means this is 0.001 inch. So to convert simple mil to inch, for example, we have 2 mil thickness. This is divided by 1000. So this is equal to 0.002 inches. So here we see we have multi-layer PCBs where the thickness of these substrates are generally given in mils, because in production we want to use the mil as a standardized unit. Mil is nothing but the 1,000th piece of an inch. So 1 inch, if you divide it 1000 times, then this is called a mil, and you can convert easily anything from mil to inch or inch to mil. You can convert even from millimeter to mil as well, but in production or in Gerber file or designing a PCB, you follow all measurements in terms of mils. So all the substrate thickness as well as the thickness of traces, thickness of the holes, vias and so on, everything is in the mils. So now let's discuss what PCB is actually made of. So a basic PCB starts with a copper clad fiberglass material or thin copper sheets attached to either side of the board. Consists of copper foil, copper plating, solder flow, solder mask, traces and slots and cutouts. So this PCB, which is the printed circuit board, is made up of the fiberglass copper clad material. Fiberglass is the substrate which is insulating in nature, and on both the sides we put either copper cladding, it means we deposit copper with a very small thickness and we etch out the copper selectively, or we can take a film as well, a very thin film of copper, and we paste it over this insulating substrate. This is how we make the PCB. And there are two technologies as we earlier discussed. One is through hole technology, one is the surface mount technology, where in the through hole technology we had this resistor which is coming two lead wires. We have to dig the hole or the put PTH or put through hole on the substrate to put them in place. In surface mount technology, we need not to put the holes, we just have landing pads. On them we put our component, heat it up so that it gets connected. So these are two types of technology for which PCB is made. One is the through hole technology, one is the surface mount technology. Let's write it down. So there are two types of PCBs. The first one is through hole technology. In this technology, these are the first PCBs actually used for mounting electronics. So that we do mounting of electronic components by lead inserted through holes on one side of the board and soldered onto copper trace on the other side. So this is through hole technology. The other one is the surface mount technology. So here the components are mechanically redesigned to have small metal tabs or end caps which could be soldered directly on the PCB surface. This does not need PTH or put through holes. So we have two types of PCBs technology available. The first one is the older one, which is through hole technology, where any component we want to put on PCB, we have to dig two holes in the PCB, and those two lead wires, for example, one resistor has two terminals, one on the left, one on the right. These two lead wires need to go through the holes, and we soldered or on the other side, which is the bottom, we solder it on the track. These tracks are on the bottom side of PCB. So we have to, the number of components, the double of the holes we need to make on the PCB. So this is the older technology. However, the latest technology is surface mount technology, where we need not to put any holes. We draw the pads on the PCB on the top surface itself. We have two pads and we put the component. Component is special, which is not suitable for through technology. In this case, the component does not have lead wires, it has just the metal cap, small metal piece attached both the side. You put the component on the landing pad, which is very suitable dimensionally, it is exactly same as the component size, and you just heat it up. So when you heat it, the solder actually melts and make an electrical connection on both the sides. So this is surface mount technology. This is very much used nowadays for a large number of components if we have in the circuit. So this is the types of PCB. Let us see what PCB base is actually made up of. So PCB base, which is green color substrate, the base material of substrate is fiberglass. FR4 is usually used. This solid core gives PCB its rigidity and thickness. There are also flexible PCBs. Built on high temperature plastic. And what is this FR4 substrate? FR stands for flame retardant. This is a composite material composed of one fiberglass cloth with an epoxy resin binder that is flame resistant. So in PCB we have a base material which is fiberglass substrate. FR4 is the commonly used material for the PCB manufacturing, which is a low cost substrate compared to the other high frequency or the expensive substrate. However, this FR4 is a solid PCB, it is not kind of bendable. However, there are other PCB materials available which are used for in wearable electronics also, which are flexible. You can bend these substrates. So, the electronic circuit which is there on top, that you can bend it, and these are made upon high temperature plastics which can be bent. Mostly we use FR4 substrate. FR4 actually stands for flame retardant. This is the property of this FR4 substrate. If we use it in, let us say, high power, high temperature applications, this is actually retardant to flame, which is a very good property for electronic circuit. It should not catch fire while exposed to the high temperature or high powers. And this FR4 is nothing but a composite material composed of woven fiberglass cloth. So, this is a kind of cloth which we put epoxy resin on this and we freeze it. So, this becomes hard, and now you can use this FR4 substrate as electronic PCB assembly. You can make your circuit, you can design your circuit in software, and for actual hardware you take this FR4 substrate, put the traces on top and bottom, and you can place your electronic components to make a complete circuit. So, this is how we make the PCBs. So, this is all for today. Thank you.